Hi, my name is Martin Smith, and I'm here to talk about interference. A few videos ago, I did one about a lie in physics, and that is the lie about thermodynamics. In 1984, basic physics, first year physics, we had to calculate the efficiency of a gasoline engine. And through thermodynamics, as it expands, it cools down, we lose energy because it cools down. There's a lot of other things that we lose energy on through the expansion of gases. And thermodynamics goes over all that stuff. And we came up with about 4% efficiency for a gasoline vehicle. Now these vehicles, a standard vehicle was about 3,000 pounds and got about 24 miles to the gallon. Nowadays they're claiming that gasoline vehicles are getting 30% efficiency, and yet they're still getting around 24 miles to the gallon. So there's a lot of lies in physics, and the interference, the double slit experiment is one of those lies, but it is a lie of omission. And on this omission, there's other types of interference going on that's not being talked about. The basic spin interference, edge interference, reflection, 2D interference, 3D interference, and thin slit interference are the 6 that I have been able to directly observe, and I'm going to go over those today. Starting with spin interference, this is what we see with the double slit experiment, and we have 2 small slits. So what we're looking at is an interference that is approximately 2.3 millimeters at 532 nanometers and approximately 15 meters from the double slit to the wall or surface that it's being viewed on. So as the wall comes closer, if you bring it in half, the distance between the interference would also be cut in half. So this is where I figure that it is a spin. How confident am I of this? If I had put money on it, okay, green laser has 532 nanometers, or if back when I was taking a physics of color light at NC State, North Carolina, they only used angstroms, so it'd be 5,320 angstroms. Some people will only work in angstroms, which I found out. That would be the equivalence of that in meters. That'd be 6 zeros before the 5. And here I'm dealing in millimeters on the wall, so I'm going to go ahead and break this down to millimeters. That means to say that 0.000532 millimeters. Every time it goes through there, this green laser of 532 nanometers, the photons do 1 complete spin. So if I take the hypotenuse, the cosine, and the sine, and use the formula a squared plus b squared equals c squared, I'm going to change it around to c squared minus a squared equals b squared. So I'm going to take the hypotenuse, put it here and square it, take the cosine, put it here and square it, and that's going to equal b squared. So I come up with this number, I take the square root of it, and I get 2.3 millimeters. And that is pretty much what I see on the wall. Edge interference, I'm only guessing at this one, but I have a feeling, or I suspect, that as photons get close to a surface, they have an electromagnetic effect as they are spinning. And that spin makes them hit the wall, reflect, hit the wall, reflect, and where it hits the sides, they're going to have a reflection interference, and it's going to put it in different places. And that is my best guess. I wouldn't even put 50-50 on that one, on my guess. Okay, this interference is shot through a square hole, and as you can see, the larger interference has to be coming off the sides because the sides are square, and it is showing that. I guess this one here, I don't want to just say this is the way it is because that's a bit of a Chicken Little effect. The background on that is a story, children's story, a newborn chicken, and everyone called him Chicken Little, according to the title of the story anyway. Has a raindrop fall on his head, and he assumes automatically that the sky is falling. A lot of physics delves into that type of thinking, and I want to stay away from it. So I'd rather put percentages of what I think the percentage is of my idea being correct. This one I'm going to put 1 out of 10, and this is reflection interference. On this one, I am getting weird shapes on the interference. And what I notice is that when the background changes, these shapes change. And that's about all I can really put on it. But I still notice that it is a different type of interference than any other. The 2D interference, that is where I shine a light, take a laser, shine it across the room, hit the paint on the other side. That paint has an interference pattern within itself. That interference pattern collects and creates a secondary interference on the other wall. So as you look at it, you will see dots in particular view, but as your eye or your camera moves around, those dots stay in the same place. So I'm calling that a two-dimensional interference. A three-dimensional interference, you get that when you look through a picket fence. And I drive by a picket fence every week, and I notice the effect. It's anywhere from 20 to 100 pickets, and that effect has to do with the distance, how thick the pickets are, how far apart the pickets are away from each other, and how far the two picket fences are away from each other. So there's a lot of aspects that interfere with this. Now, on this 3D interference, what's happening is you'll look at the wall, and this would be within the laser itself. So if you go outside that first dot, you won't see it. I have seen it before one other place, but I don't remember how I did it. This is the experiment that I was able to recreate. And as I moved my eye around, where these dots were became in different places. So what I'm saying is that the light's hitting this from different angles, and those angles are reflect differently in different places as you were looking in a picket fence. And this one here, basically I drive by a picket fence and I notice a wave pattern through the pickets. Going up here, back up here, the gases are a different spacing than the atoms in the lens, and I'm assuming that these two spacings are working similar to pickets and creating different outcomes on the wall and different outcomes for how you see it, so that when the light hits something, if it's it has a wavelength so that it goes out in certain patterns. So it'll go out here, but not here. And this is something you see in antennas also. The thin slit interference, I'm going to show you an example, but quite honestly, I don't even have a clue to make even a guess. Now, some of the others I did guess at. Even if I only gave it a 1 to 10, I was at least able to guess at it. This one, I'm absolutely clueless. I cannot think of anything that would create it. So you're on your own on that one. But these are observations that I have made, and it should be said that there's different types of interference. Okay, not a Brita commercial. This is showing same setup that I had before. Block gauges, lapped finish, and a green laser going through them. Yeah, quite a bit different through the camera than it does by the naked eye. You can barely see those two lines dividing it. So it starts off with two lines, goes down to one, and they sort of alternate and crisscross. And down towards the bottom you can't see these lines, but they are there. Those lines just keep going. And there's also long lines going between. Now the strange thing is the slits are going a 90-degree angle from the screen line that we're seeing right now. And this is a different type of event that this laser is doing, so I'm putting it through a real thin slit, approximately 0.2 of 1/1000th of an inch, and that's all the light that's getting through. And this is pretty much how it is seen outside, is a long sliver. Sort of weird, don't know.